Swayam Prabha. Digital India. Educated India.
Okay, thank you for letting us to have an opportunity to present our work. It is a very simple simulation study on absorption of ozone and VOC ozonation in a rotating backpack. This is a joint work between National Tsinghua University and National Yunnan University of Science Technology that is represented by Professor Jia-Ling Kang. And he is actually the main contributor to this work, but he's having a class right now, so he cannot make the presentation himself. Utilization of high gravity to enhance mass transfer in a rotating backpack, which I'll call RPB later on, has been a very well-known process intensification technology. The application of RPB to improve the efficiency of ozone degradation of volatile organics has been studied extensively in the literature recently, because the problem with ozone oxidation is that it is very difficult to get ozone to be dissolved in the solution and affect the oxidation. But in these experimental studies, each person developed their own empirical correlations, and there is no way that we know that whether the models are consistent between each another. So in this work, we propose a generic model that can describe oxygen and ozone absorption in the experimental data, as well as using those data to develop the model that is for mass transfer and ozonation of volatile organics. And two examples, autocresol and phenols, are used as a validation examples. Okay, and also, but in addition to developing the model, we want to explore the key factors influencing this process. The model for RPB is very simple. It's a one-dimensional spatial temporal model that accounts for the mass transfer, diffusion, and reaction in the system. But there are two key factors in this model. One is the mass transfer between the gas phase and the liquid phase, and the other is the reaction in the liquid phase. But reaction in the liquid phase are usually well studied using independent batch types reactions. So the key is whether those reaction kinetics can be used in conjunction with mass transfer model developed for RPB to properly describe our process. For RPB mass transfer, usually we model the mass transfer rate as an overall gas phase mass transfer coefficients times the pressure gradient. The Pi is the pressure of the component in the gas phase, and Pi star is the equilibrium partial pressure at the gas-liquid interface. And the overall mass transfer coefficients are influenced by two factors. One is the gas phase resistance, and the other one is the liquid phase resistance. However, the liquid phase resistance, because of reaction, instead of regular liquid phase mass transfer, because of the reaction, some of the materials will be consumed near the interface, creating a film. Okay, and the reaction will will increase the mass transfer, and this factor is known as the enhancement factor. So in developing a mass transfer model, the key is which types of liquid phase and gas phase mass transfer we use, and how to describe or model the enhancement factor. The equilibrium is pretty simple. If it is non-volatile components, then it is described by a solution model. If it is incondensable fluid like nitrogen, oxygen, and ozone, they can be described by the equilibrium between gas phase and liquid phase can be described by the Henry's law. Okay, let us return to this mass transfer coefficient. The definition of the enhancement factor is the liquid phase mass transfer coefficient for absorption with chemical reactions over the liquid phase mass transfer coefficient for absorption without chemical reaction. For those gaseous components that has no reactions, we can do experimental models, do experiments, and develop the model for the liquid phase mass transfer coefficients for absorption without chemical reactions. But for system with chemical reactions, then we have to find kinetics and the proper kinetics that can describe the enhancement factors. So we look at absorption of oxygen and ozone. The data were provided by Professor Chen at CYCU in Taiwan, and also the group by Liu et al. on ozone reactions. Okay, and these are the common mass transfer models proposed for gas phase absorption, listed in the, wait, what happened? Okay, that is proposed in the literature trying to describe gas and liquid mass transfer. Okay, these are common, well-developed mass transfer coefficients. Okay. For oxygen absorption, it is very clear that oxygen alone will not react in the liquid phase. So this would be a very good system for us to validate what kind of gas and liquid phase mass transfer coefficients that are appropriate. And according to the experiments, we found that the model proposed by Chen is very good, much better than the older liquid phase mass transfer coefficient proposed by Tong and Ma a number of years ago. And this is a particularly good experimental system for validating liquid phase mass transfer coefficient, because all Chen did was to change the liquid phase mass transfer coefficient. Because if you test our models, most of the resistance are in the liquid phase. There's negligible, if we neglect gas phase resistance or include gas phase resistance, the model prediction are exactly the same. So this model is dominated by, this experimental system is dominated by liquid phase mass transfer, and it is a good system to look at pure liquid phase mass transfer. Oh, sorry, the title is, so if you use this liquid phase mass transfer and look at the enhancement factor for ozone absorption. Okay, now we have ozone absorption, and ozone will decompose in water, and we find that zero order decomposition reaction is very good describing the model with the Chen model for liquid phase mass transfer, which is the Chen model gives an average of 70%, which seems large, but these experiments are very difficult to perform, and experimental errors are very large. Next, please. So after we have established the mass transfer, the liquid phase mass transfer model, and for oxygen and ozone, we look at autocresol. Okay, the overall reaction of autocresol is like this, and experimental data was also provided by Professor Chen and his co-workers in 2005. But if we do the same thing to the model, and we find that if we assume that there's a first order enhancement by VOC, the results are completely off the chart. Okay, actually, the predictions are much higher than the experimental values. Next, please. Okay, it turns out that the kinetic parameters provided by the experimenters are done using exit buffer by using phosphoric acid and sodium hydroxide. Okay, so the actual reaction is not the actual detailed mechanistic step is not a reaction between ozone and the VOC, but it involves intermediate reactions between the ozone and the acid. So if we just replace the ozone concentration, the VOC concentration with the phosphoric acid concentration, the results becomes very good. Okay, so this is for the ozone, autocresol system. Next, please. We do the same thing for the phenol system, and the phenol system, the data was provided by Jun and Itel in 2012. Next, please. And again, if we use phenol as the first order enhancement factor concentration, we find that the experimental data, the model predicts under-predicted the experimental results. So again, using the VOC concentration itself does not work. Next, please. It turns out it is also an acid-catalyzed reaction, and sulfuric acid was used, okay, at various pH. Okay, they actually provide pH data for different sulfuric acids, and we can use this and use the same reaction constant, but instead of using sulfuric acid, we use the concentration of the bisulfate and the sulfate ion. We can get excellent agreement with experiments. Next, please. So in conclusion, we have proposed an RPB model that can predict the phenomenon of ozonation of VOC in the RPB. Okay? And absorption of ozone and oxygens are dominated by liquid phase reaction, and the mass transfer is best described by the correlation proposed by Chen and Itel in 2004. In VOC or ozonation, they are catalyzed by exit. So instead of a first order enhancement factor for using the VOC concentration, we actually find that we should use the first order enhancements of the exit as the first order enhancement, as the concentration calculated by the first order enhancement in the enhancement factor. So this is the key to modeling ozonization of VOC in RPB. Thank you.
Thank you, Professor Cheng. Any questions? Yeah, so I have one small question. So you talked about instead of VOC concentration, we should talk about incorporate acid
Concentration, yeah.
So, but in one place we are directly using one ion,
Yeah.
and another one in a sulfuric acid you have a two.
Right.
And so how do you decide? Because it depending on the different acid, things can change.
Yeah, but the kinetic constant we use are obtained by those experiments using different acids. So they already have proposed a K value, okay, for those reactions. But the reactions is written, the overall reaction is written as reaction between ozone and the VOC. But if we use VOC concentration and use these kinetic values, it doesn't work. So instead, we find out that if we use the acid concentration but use the same K values, then we are okay. So that means the key step in enhancement is a reaction between the ozone and the acid, not between ozone and the VOC.
Okay, so I have to write equation between ozone and acid also, and find the kinetic parameters for them too.
No, we just use the overall kinetics and assume that we. Why this is not is still a mystery to me, but we can just look at, because if we are not actually calculating the reaction in the liquid phase.
Okay.
We are calculating the effect on enhancement on the liquid film mass transfer.
Okay.
So on the liquid film, you can see that the acid will be rapidly depleted, and this create the enhancement effect. Okay. So we don't need a detailed model in terms of acids. Luckily, we can just use the acid concentration as in our model parameters. Okay.